So today what we're going to do is keep looking at limits. And last time when we were looking at limits, we looked at limits in terms of it being numerical, or looking at it in terms of being graphical. And that kind of gives us a good idea of what a limit is. In a nutshell again, a limit describes the behavior of the function as you start approaching some particular value. Okay, and the way that we denote that, so we'll say the limit as x approaches some particular value a of some kind of function f of x, where f of x might be a polynomial, might be a rational function, some transcendental function, some kind of function. And we just want to determine what's happening to the values of f of x as x approaches the value of a. Now, the way that this is defined as a two-sided limit. You gotta remember, you got to approach it from both directions. Or you can say it has to approach from all directions. You can think of it like that. And in 2D, that just means, okay, left and right. Okay, so when you see this, you do have to, it is your responsibility to check that it goes from the left and also if it goes from the right. Okay, you might get L from the left side, you might get R from the right side, and in the event, if these two things, if they are equal, or L does equal R, then we say the limit, it does exist, and moreover, the limit is going to be L, that value. If you do not have these two conditions, then the limit does not exist, and you can't say this anymore. So the only reason why you can say this is because the left and the right are identical when you look at the limits. So whenever you're taking limits, you're going to see something that's going to keep occurring time and time and time again. You're basically going to have three different cases when you start analyzing algebraically, looking at it analytically. Okay, it is entirely possible whenever you're going about this process, you might have some kind of rational function. That's possible. You might get some kind of number over some kind of number. Okay, in that particular case, there's not much of an issue. You just kind of go with it and you're essentially done. The problem comes about is when you start getting into those really strange cases. Okay, if you get a case such as you have a number over 0. Okay, what's happening then? Or if you were to have 0 over 0, what's going to happen then? So you get to these cases down here, you have to slow down just a little bit to make some kind of observation as to what is really being played out. Okay, so again, I'm looking from the left, I'm looking from the right. I just want to see what's happening as I approach the value. And I can do this numerically. I can pick some values, I can plug them in. I can also look at it graphically, but I got to know the graphs. If I don't know the graphs, it's going to be really hard for me to do it graphically, so it'd be a good idea to know graphs. So this graph, 1 over x, this is one of these graphs that, yes, guys, you really got to know this graph. It is very useful, especially as we dig deeper into limits. You start looking at some things with calculus. So the graph of 1 over x, it looks like this. I can plug in anything that I want, and I'm not going to run into any issues except when I plug in 0. Because as soon as I plug in 0, I'm going to get something like 1 over 0. And what is 1 over 0? Well, it's complicated, let's say. Well, again, when I'm looking at limits, again, I'm just looking to see how things are, how they're progressing. And right here, I don't see any problems with the graph. I don't see any breaks in the graph. I don't see any holes in the graph or anything like that would cause me some kind of alarm to slow down. So as I approach it from this direction, I'm on the curve and I'm sliding down, and I'm approaching from this direction, I'm going up this way. And as long as those arrow tips, if they touch, okay, then the limit's going to exist. That's how we do this graphically. And they're going to touch exactly whenever x equals 1, which is going to get you to 0.11. Okay, so in other words, if you don't have any breaks in your graph, the way that you could go ahead and assess the limit is just push that big red button and do a substitution. Take the value, plug it in. Now, there are reasons why that's the case. That's not how we assess limits, but there's some properties. It's a property known as continuity, and we'll talk more about that next time. But just for today, what we're really trying to do is just trying to get a good feel of how to actually compute limits. Then we'll take a step back and ask ourselves, okay, why do we do what we do? Why do we actually do this? And then we'll go back and compute limits again. So sometimes in order to understand something, you got to get your hands dirty. You got to start working through the problem. Then you come back and you say, okay, what really happened? Okay, so from the graph, there's no breaks in it. So we can just simply take this, drop it in. We don't really have much of an issue. The issue comes about in this problem is whenever I'm approaching 0. Okay, when I approach it, I'm approaching it from the left and I'm approaching it from the right-hand side. So again, if I want to inspect to see what's happening with the limit, I got to take the graph, the limit here, and I got to look at it on the left-hand side of the graph or the right-hand side of the graph where that 0 is going to be located. So in other words, I do have to inspect left-hand limit and I have to inspect right-hand limit. Okay, well, let's just look and see what's happening maybe on the right-hand side. So if I'm looking at the right-hand side, so I'm looking at this one. And you can think about right-hand side, right hand's going this way. So you're approaching it in that direction. That's a good way, too, to remember it. I'm approaching right-hand side. Left-hand side, you're going to be approaching it this way. So the numbers are going to be going down or going up. These are going to be going down, decrementing, incrementing, increasing. So pick certain things, which is going to be helpful. Maybe things like 1. You know, that might be all right. Or how about, I don't know, let's say like 1/10. So 0.1, or about 1 over 100, or in other words, 0.01. And I can continue on, maybe like 1 over 1,000. So 0.001. And I can continue this process as these things get closer and closer to 0. And let's go ahead and just plug it in numerically. So if x corresponds to 1, or 1 over 1, or excuse me, 1 over 10, or 1 over 100, or 1 over 1,000, and I'm looking at the function 1 over x, if I was just to do an evaluation, okay, I'll get 1, and then I get 1 over 10. What do I do to simplify that kind of fraction? I want it in terms like a over b. I don't want a fraction over a fraction. It's a little complex. So we can do a whole entire keep, change, flip. You guys remember that? Where if you have a fraction and it's being divided by a fraction, what we're going to get here, you can express it as this if you like, but you keep the first fraction in place, change the sign, and then you flip, look at the reciprocal. Okay, so that's the whole entire rule. But again, if I reduce mathematics down to a bunch of memorization without understanding, it's going to crumble very quickly, especially when you get into stressful situations. Okay, so my question is, yeah, that's true, but why is that true? Why can I say that? Or do I just have to accept it on blind faith and don't worry about it? Well, you want to look at the logic. We want to make sure that we're really understanding. We got that good foundation so you can keep building understanding on top of understanding on top of understanding. So in this particular case, we have a over b, c over d. And if you like, say something like 3 over 2, 5 over 7. It's going to echo the exact same thing. What you could do here is you can multiply this by whatever you like. You can multiply this by 2 over 2 if you want. because 2 over 2 is going to get you a value of 1. So it's not going to change it up. So you can multiply it by whatever you like, provided that the fraction is 1. Or you can say 3 over 3, because what's 3 over 3? It's 1. And 1 times a fraction is not going to change the fraction up. You can also say 2/3 over 2/3, and that still is not going to change the fraction up. But what I want to do, here it is, I have a problem. And the way that you solve problems, guys, is you first have to identify the problem. How will you ever solve a problem if you can't identify what the problem really is? You guys ever think about that? So you look at it and say, okay, I don't like this. Well, why don't I like it? Because I don't want that fraction right there. I want it to go away. So what can I do to make it go away? Well, I can multiply it by its reciprocal. Because when I multiply by the reciprocal, I'll have CD over DC, and that's just going to correspond to 1. But I just can't multiply the denominator without multiplying the numerator, because again, I got to make sure that it's 1 when I'm multiplying the fraction. So this fraction right here equals 1. So when I multiply through, we're going to have AD BC, and this is equal to 1. And that's why when you look at a fraction divided by a fraction, you keep the first fraction in place, and you take what's down below, and you flip it, and you multiply through. Commonly known as a good old keep change flip. Well, over here, I have 1 over 1/10. Where's the fraction I was talking about, the A over B? It's right there. So if I don't have it, I can construct it. I can make it. I can express 1 as 1 over 1. And then if I do the exact same process, keep the first fraction in place, flip the 1 down below, I see fairly quickly now that this value, this evaluation, is 10. Okay, do the same thing right here. Okay, you can take it, plug it in, do a keep change flip. Okay, I'm going to see fairly quickly also that's 100. And then when I do it with the next one, 1 over 1,000, okay, we're going to get 1,000. And I'm really starting to see a pattern here, aren't I? If I keep making this thing a little bit smaller, then what happens when I do the evaluation, it gets a little bit bigger. So as one goes up, the other one goes down. Okay, well, that kind of makes a lot of sense when you start thinking about what really is a fraction. If I was to have 6 over 2, well, 6 over 2, that has to be a value of 3. Okay, and the question is, again, not so much what is the right answer, but why is that the right answer? And when you start focusing on the why as opposed to just show me what to do, you're taking it to the next level of understanding. Well, the reason why you can think of 6 over 2 is equal to 3 is because it really is a division problem when you look at fractions. So if I have 1 divided by 10, or if I have, let's say, 1 divided by 1 over 10th, this is saying you're taking one thing and you're chopping it up into 10 different pieces. Okay, when you have it like this, the value down here, that's getting closer and closer, really, to 0. And in order to really make it spread out, this one thing, well, it's got to go to a lot of different places. It's got to be really dispersed. Okay, now, when you look at it graphically, 1 over x, as you approach it from this direction, what's happening? It's kind of like Superman. Up, up, and away. You just don't ever stop. It goes up towards positive infinity. So in this particular case, this, as we get closer and closer to the value of 0, this is growing without bounds. You can grow without bounds in the positive infinity direction, but you can also grow without bounds going towards negative infinity. Okay, and if we were to set this up and do the exact same thing and say negative 1/10, negative 1/100, we'll get the same kind of analysis here. We see that the value is getting bigger and bigger and bigger. So this is going to go towards negative infinity. Okay, so here's the deal. Whenever you're assessing limits, and this is for one-sided for the moment, if you're assessing one-sided limits and you make the observation that you're getting this, two things are going to occur. Always two things are going to occur. It's going to go up towards positive infinity or negative infinity. Okay? And again, that's really just for one-sided limits. Okay? Now, if I was to look at the two-sided limit, in order for this to exist, the left side and the right side, they have to meet, right? They got to go to the exact same spot. If they're not going to the exact same spot, the limit doesn't exist. So when I look at the graph, I can see fairly quickly that this one is shooting straight up, the other one's going straight down. Am I going to the exact same spots? No. So what that says then, this doesn't exist. D and E. Now, there's a little bit going on here too. You know, could you actually really get to positive infinity? No, not really. So it's kind of like a type of limit that doesn't exist that we can at least quantify as type of being kind of an existence. Again, don't think too hard about it, but you might see things like that from time to time. You're not really ever getting to infinity, but you know, limits again, they're not saying you will get somewhere. It's just saying what's the behavior of the function as you're approaching some particular value. What are the trends? What is it going to start looking like? And as you get closer and closer to that vertical asymptote that you learned about back in pre-calculus, right there at 0, this thing's taking off towards positive infinity. Or if you approach from the left, it's going towards negative infinity. And the term that we use again, you say is growing without bounds. Okay, take this problem, let's make a little tweak to it, and let's say 1 over x squared. Again, I want to inspect the left side, I want to inspect the right-hand side. And I can go about this numerically once again. I can pick certain values, such as 1, 1 over 10, 1 over 100, 1 over 1,000. Now, again, just by checking the values, by no means does this prove anything, but it's giving you the intuition as to what's happening with the function. That's what that's doing. Okay, so if you take this and you plug it in, this thing is blowing up pretty fast. It's going towards positive infinity. I can see that fairly quickly. Okay, that's what the numbers are telling me. And if I was to look at the negatives, maybe approach it from the left side now. If I was to take that and square it, what happens when I square a negative value? Say it's positive. So I get the exact same thing. Okay, so what the numbers are telling me is this right here, it seems like it's going off towards positive infinity as well as that. And when I look at the graph, it makes a lot of sense. Why? Because the graph of 1 over x squared looks like that. on the right and on the left. And as you approach, coming in from this direction, going towards 0, the graph's shooting up. And as you approach it this way, it's going up also. Both directions are going towards positive infinity. Again, as long as you're going to the same general vicinity, location, the value for the function, then we say that, okay, the limit's going to exist. Could you ever really get to positive infinity? No, but you're going to the exact same spot. So it's growing out bounds in the positive direction, right-hand side and left-hand side. Okay, and if you go back and look at the graph of 1 over x, again, this is dropping towards negative infinity. This is going towards positive infinity. Your graphs, if you have 1 over x to an even power, whether it's square, 4, 6, or 8th power, that's what it basically looks like. Okay, it might be flattened out a little bit more right here, but in general, it's going to look pretty much like this. And likewise, if you have 1 over x to an odd power, such as 1 over x to the 3rd, 1 over x to the 5th, it's going to look like this. You need to know these graphs. You really need to know these graphs. They are very good analytical tools to help you understand what's going to happen with limits as we get deeper and deeper into them. And what you need to know as well is, as I approach 0, what's happening? Am I going towards positive infinity or am I going towards negative infinity? Okay, well, let me stop here. I want to see if this is making sense because this is important. Okay, so when you're taking limits, again, if you have a number over a number, there's not going to be much of an issue. There's going to be an issue, though, when you have a number over 0. And in terms of one-sided limits, you're always going to get an answer, either positive infinity or negative infinity. If you start talking about two-sided limits, it's possible. You can have 3 answers. You can have positive infinity, negative infinity, or you might run into the case of it just does not exist. So if you don't have that, make sure you got that down. That's really going to help out. One-sided is always going to be this option. So it's a coin toss, 50-50. It's either this one or this one. If it's a two-sided, it's possible that it could not exist. And a great example, again, is think of 1 over x. If you take the limit, as you go off to 0, one side's going up, one side's going down, D and E. It does not exist. When you're assessing limits, basically what you're going to do, in most cases, is push the big red button, cross your fingers, and hope nothing goes wrong. And as long as you're working with polynomials, exponentials, trigonometric functions, you're not going to run into much of an issue. So polynomials, these are really nice. Exponential equations, these are also fairly nice. You're not going to run into much of an issue. And trigonometric functions, mostly not. And primarily what I'm speaking about is sine and cosine. You're not going to have much of an issue there. Okay, you get to the things like secant, tangent, you got to slow down a little bit. You could have some issues you got to consider. Okay, so if I'm looking at the limit, for instance, 2x plus 5 as x approaches the value of 1, if I was to actually look at the graph, look at it, graphically, again, it's linear. It's going to be a line. Slope's going to be 2. It's going to look a little bit like this. And I don't really see it breaking. I don't see it being separated. I don't see any holes in the graph. It's a nice continuous graph. No issues at all. It's really just a matter of taking it, plugging it in, cranking it out. Okay, now again, I got to warn you, I can't stress this enough. Limits really are not a plug and play. but it really seems like that's what we're doing. But again, it has to do with certain characteristics which polynomials have, exponentials have, and these functions over here also have. This idea of continuity. Okay. So basically, if you have polynomial, not much of an issue. The issues come about is when I start, getting away from those. Maybe something like this. Okay, so the first thing you do, cross your fingers. That's a good math technique, isn't it? I like to do it. Please, 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 please work. Just take it, plug it in, guys. See what happens. Be a scientist. Worst case scenario, the world implodes. The universe goes down a black hole, but if the universe goes down a black hole, no one's there to see it anyways because everyone's in the black hole and that's it. So you're okay, either way. Take it, plug it in. All right, so if you plug this in, what you're going to get? You get 1 minus 5 plus 6. Okay, get minus 4. Okay, that's fine. And add that to 2 or 6, you're going to get a value of 2. Not much of an issue. Okay, but what happens though when I plug it down below? Oh, I got a problem. Okay, and again, back in pre-calculus, we said you can't really divide by 0. And I guess you kind of can in a roundabout way, but we're not really plugging in 0. We're just getting a little bit closer to the edge of 0, and we're going to see what happens to the function. Hopefully you don't fall off. Okay, so I'm talking about a two-sided limit. So I do have to inspect what's happening from the left, what's happening from the right. It is going to correspond to some kind of number over 0. And again, in these cases, you're going to have 3 different cases you're going to have to account for. Okay, it's possible it could be positive infinity, negative infinity, or it does not exist. Okay, so here's what you could potentially do. If it's possible, okay, maybe you can take this, maybe you can factor this and kind of get maybe an understanding. That's something you can potentially do. If you can't see something like that can help you out, then you can always just revert back to something that's numerical. That's also fine. Or if you know the graphs, like we did a lot back in pre-calculus, of how you graph rational functions, and you can inspect the graph, you can see how trends are climbing as you get closer to value of 1. Okay, but anyways, for this one, you could factor this. Okay, but it doesn't seem like it's going to help out too much. Okay, so in that case, when something doesn't help out, just back up and then try something else. Try maybe a different technique. Look at a value of 1. Start approaching from this direction. So you might want to take your calculator out. Okay, so maybe I'll look at things such as 1.1, 1.01, 1.001, just to make some kind of understanding as to what's happening as I'm approaching it from the right-hand side. Okay, as I keep approaching it from this direction, I'm seeing things like 8, then 98, and then 998. And I know there's 3 answers. There's only 3 possibilities. Positive infinity, negative infinity, or it doesn't exist. One-sided limits, you're always going to have 2. Positive infinity or negative infinity. What do the trends look like? Positive infinity. There we go. Okay, and then we'll do the same thing. We'll look from the left-hand side. Okay, to see what might happen coming in from this direction. And again, I might pick things such as 0.9, 0.99, 0.999. Okay, and what I see here is I get roughly about negative 12, negative 102, negative 1,002, and I'm starting to see a pattern. What am I seeing? It's getting very close. It's growing towards negative infinity. Okay, so this side is doing this. Okay, so what that means is one side's going up, the other side's going down. They're not coming together. So this would indicate the limit does not exist. Okay, so again, when you're assessing limits, polynomials, you're not going to have an issue with. Exponentials, okay, you're more likely also not going to have much of an issue with. The issues are really start occurring when you have a number divided by 0. If you were to just take that limit value, whatever it is, take it and plug it in. Okay, so the first thing to do when you look at a limit, push the big red button, cross your fingers, and hope nothing implodes. Just plug it in. See what happens. Live dangerously. Do some math. Okay, so if you take -2 and you drop it in up top, what's going to occur? You get 4 minus 10, and you get 6. What do you get? 0. Okay, that's not a problem. I can definitely have 0 in the numerator, no issues at all. You know, if I have something like 0/2, that makes complete sense. You take all of nothing and you divide it into 2 pieces of nothingness. Like, watch your hands. Take this. How much do I got? Still nothing. Makes sense. Okay, so let's see what happens down below. And if I get a number down below, I'm okay. I'm not going to be worried about anything. I know this is going to correspond to 0. Okay, so down below, we're going to get a value, take -2, drop it in, you get 4, and then we're going to get +6, and then, uh-oh, kaboom! Something happened! 0. Oh my. If you take all of nothing and you divide it into nothing, what do you get? I don't know, it's kind of like a creation account. It's like there's nothing to begin with, and it goes, something is like, nothing is like, blows your mind. You're like, oh, what's going on? Okay, so I got to think about this a little bit more. And I got to ask myself, in these kind of situations, in particular, whenever I'm working with rational expressions, I got 0/0. But again, guys, don't focus on what is the correct answer. Start training yourself to start thinking about why that is the correct answer. You unlock that, you unlock a lot of mysteries. So why did I get 0 in the numerator, and why did I get 0 in the denominator? What's a polynomial? Okay. And if I have f of x, for instance, as corresponding to x squared plus 5x plus 6, and if I have g of x as x squared minus 3x minus 10, why was it the case that whenever we dropped in -2, we got 0 for the numerator and for the denominator? So if I looked at this a little bit closer, so why did the numerator and why did the denominator both 0 out? Can you see it? There's a common factor. So whenever you have 0/0, like right here, and you're talking about, this is important, you're talking about rational expressions, where you have a polynomial over a polynomial, you're probably going to be able to divide out the common factor. That piece that's problematic, that's throwing it off. Okay, so once this divides out, then push that big red button again, cross your fingers, and hope it doesn't explode this time. Drop it in. So -2 plus 3, okay, we get 1. And that's great. I'm okay with 1. Even if I have 0 down below, I'm still okay with it. I can get some kind of answer. I just can't get an answer with 0 over 0. I got to inspect it a little closer. Okay, so take the -2, drop it in, -7. I'm good. I'm good. So as trends continue, I had a little bit of a hiccup right here at -2, but I divided that problem out. It has some kind of point of discontinuity, but if I removed it for a moment, I see what's going to occur. Okay, suppose you want to find the limit. To find the limit, what do? Cross your fingers. Push the button. Hope nothing implodes. Take it and plug it in. Just see what happens. And again, if you get a number over a number, as long as the number's not 0, okay, you're okay. I mean, you're good to go. There's no problems. The problems arise whenever you take it, you drop it in, you get 0, or you get the case of 0 over 0. Those are the 2 cases you got to slow down on. Okay, in this case again, 3 things are always going to occur. Positive infinity, minus infinity, or it doesn't exist. And these 2 cases are always going to be what you're going to get when you look at the one-sided limits. When we look at the two-sided limits, that's what this is. You're looking from 2 sides. You got 3 possibilities to consider. When you have 0 over 0, there's a lot of possibilities. This thing can be 1, it can be 2, it can be, or maybe like -1 over 7. You don't really know until you know what you know. So you got to roll your sleeves up and get to work. Okay, so let's just take it, plug it in, hope for the best. Up top, what we're going to get is 2 plus 1 minus 3. Oh, I don't really like the way this is going, but okay, that's 0. And down below, 2 minus 7 plus 5. Oh, okay. 0 over 0. Okay, so when I come into these situations, when I have 0 over 0, when I'm looking at rational expressions, this is kind of telling me, okay, I need to slow down, and I might want to go ahead and factor the numerator and the denominator. Okay, so it's going to be a quadratic, so it's going to be factored in linear terms. And I just got to kind of see how things are going to be played out, how things can be constructed. Okay, check that. X times 2x, 2x squared. Okay, then you're going to have x and 3. You're going to have minus 2x. Okay, you get positive x. Okay, you get minus 3 at the end as well. So that checks out. And then 2x squared. Then you're going to have a minus 5x. And then you're going to have a minus 2x, which gets you minus 7x. Okay, so it factors. We got it. Okay, I can see again that the reason why we got 0 over 0 is because of this cog that got stuck in the engine, this x minus 1. Factor this out, divide it out, then go ahead and check again. What would happen now if I took 1 and I plugged it in? Okay, I'll get 5 up top, which I no longer have this issue. I can have one of these 2, that's fine, but I no longer have this issue. And down below, we're going to have 2 minus 5, so we have minus 3. And I got a number, we're good to go. So whenever you have 0 over 0, guys, it could be something like 5 over negative 3, or it can be 1 over negative 7, or it could be 1, it could be 2. That's why whenever we see 0 over 0, it's known as a I don't know what it is form. It's called an indeterminate form because you're not really determining what it is. Okay, but anyways, what you need to make sure you guys know here for today is you got to make sure you're okay with taking some limits. And again, we're taking limits of polynomials, not much of an issue. Push that big red button, substitute the value into the polynomial, evaluate it to the very end. The issue again is when you start running into these kind of situations where you have to slow down a little bit more, And if you have a number over 0, 3 cases you've got to consider, as long as this number again is not 0. And if the number is 0, 0 over 0, okay, a good strategy is to go ahead and look at how the numerator and the denominator might factor. So next time what we're going to do is we're going to keep digging more into this, keep looking at some more limits, looking at them algebraically, looking at some more complicated systems, and see what we can do to help speed up the calculations a little bit more when looking at these kind of scenarios. You guys have a great day, and I'll see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.